Okay, the reason we're laughing is I was singing something in the background and then all of a sudden noticed it was noontime and hit showtime. And I
Showtime.
think both Dave and Jason were figuring, okay, he's going to finish singing the song. And I said, no, 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 I'm not going to do that. So, well, anyway, inside joke. Sorry, folks. Welcome to Takeo Tuesday for July 22nd, 2025. And a happy good morning or good afternoon to each and every one of you, wherever you may be. John Barba here, along with Jason Cox and Dave
Hello.
Holdorf. How we all doing, gentlemen? Are we psyched and ready and prime for a great Takeo Tuesday?
Of course,
Absolutely.
man. It's just another one of them great days out today. I mean, it's gorgeous weather-wise. Yes, I'm indoors, so I can't. It's really hard to do Takeout Tuesdays from outside. I've tried. I can't see the screen, sitting in the sun and anything like that. So it gets challenging and very distracting out there. So
Are you
yes,
guys beating the heat out there on the East Coast? I heard it was really hot there for a bit.
Last week, very much so. This week, it's been gorgeous,
Awesome.
absolutely gorgeous.
Awesome.
It's
yeah,
the kind of gorgeous that makes you wish you didn't have a full-time job. That's how
Yeah,
gorgeous it
right,
was.
yeah,
right.
the temperature's
Excellent to
been
hear.
killers. The humidity has dropped down. So therefore, but it's coming back by Thursday.
Well,
Yeah.
Oh,
we
joy.
live
How good for us.
in that.
That's right. So let's talk
All
about
right. Hey,
PDH
well,
circulators out there, right? So we got a
there
couple
you go.
jumping on board, Michael and John saying, "Hey, man." So
Yep.
John's all excited for another Takeout Tuesday. Excellent. Thank you.
Excellent, excellent. For those of you who just joined us, if you could do us a favor, go to your questions chat section. Just say, give us a hi and a hearty hi and welcome, and then just let us know where you're coming from, so we know where you're checking in from and what our reach is. So we'd love to hear from you. And also during the presentation, we do invite you to ask questions as they occur to you. We'll take breaks periodically to answer those questions and address them. But do me a favor, guys, just go right to your question chat section and just chime in where you're, who you are, where you're from, and what you're hoping for today. We'd appreciate that. So Jerry chimed in. We have John. There's Ken
Canada.
from Red Deer, Alberta. We've got Alan from
Ooh, we
out
got
your neck of the
Oakland.
woods. Jason from
Yeah,
Oakland,
my
California.
Bay
Excellent.
Area homie. Welcome.
All right. Excellent. Fairbanks checking in. It's nice and cool there. I think it always is, right? That's cool. One of my favorite cities. The coldest I've ever been was in Fairbanks, Alaska. We went there in January to do a training, which really didn't make any sense. Never saw the sun, and I think it was 47 below zero. That was
Wow.
insane. That was absolutely insane.
Oh, we
But
got Mike
anyway,
from
we got
Portland,
Robert from
Oregon too.
Brattleboro.
Yes,
Hot
Robert,
dog,
I
hot
did see
dog.
your email. I was been a little tied up yesterday and today, so I did see your email, and I will be getting back to you real soon.
Very good, very good. And Colin's checking in as well. Great. Let's get started. We're going to talk about a subject that's near and dear to my heart: flow, head, and the finer points of circulator selection. In the residential world, you guys know this, my compatriots, and I think you guys out there in the field know this. The go-to circulator in the residential world for the past 50 years has been what? What has been the go-to? I'm not thinking about it. I reach on the shelf, pull it off, and stick it in a job. For the past 50 years, what has that circulator been? Yep, you guys know it. Yeah, Warren knows it. Robert, yeah, the Takeo 007. It's been the industry standard going back to its debut in 1975. Why? I guess the question is why. Jason, why? Dave, why has it been the go-to circulator for 50 years?
Is
I've
that a
left them.
rocker?
I've left them stunned in silence. Wow.
Because you can grab 3/4 inch pipe in a 007 and do darn near anything.
There you go. It just fits. Is it oversized? Most definitely, yes. It's most definitely oversized for most applications. But for much of those 50 years, we really A, didn't have a choice, and B, we really didn't care. Oversizing a circulator had very small, if non-existent, or non-noticeable. I'm not going to say non-existent, but I'll say non-noticeable downsides to it. All right. Yeah. Okay. If we overpumped, we never saw a 20-degree delta T on a big old cast iron boiler with a lot of mass to it. Not a terrible thing. It's not a great thing, but we could survive it. Nobody ever called us because they were cold, and it was our fault because we undersized the circulator. So life is good, right? Life is good. With the advent of lower mass boilers, particularly modulating condensing boilers over the past 20 years, and now going into things like air to water heat pumps, that oversizing now brings with it some issues. And those issues include short cycling, repeated wearing out of components because they're short cycling. And that short cycling brings with it a real negative impact on overall system efficiency. None of these are good. The advent of ECM and variable speed technology has given us a window into more deeply understanding those problems and finding ways in which we can mitigate, reduce the effects of those problems, if not eliminate them for the most part. So all of those things have been a very interesting development over, I'm going to say, the past 20 years with ModCon boilers and maybe the past 10 with ECM circulators. Which brings us to today's session. We have to go back to the basics of understanding flow, understanding head loss, and understanding how a circulator fits, and understanding what some of these ECM things do, and more importantly, what they don't do. And that's the point of today's session. We want to talk about flow, head, and the finer points of circulator selection, and understanding that ECM does not automatically give you a pass on this stuff. We got to understand that. So let us get started. One of my favorite concert tours ever was Neil Young and Crazy Horse back, I'm going to say 79, when they did the Rust Never Sleeps tour. Hey, hey, my. Great stuff. Absolutely great stuff. Rock and roll will never die. The thing about that concert tour, that song in particular, that makes it applicable to today. It's not just because I'm a rocker having a flashback. Okay, there's a reason behind this. There's more to the picture than meets the eye when it comes to circulator selection and variable speed. A lot of people say, hey, you put a variable speed pump in there, put in each, it'll take care of everything. It'll take care of everything. All you do is push the button and everybody's happy. No, none of those are true. You still have to understand these fundamentals. So yeah, there is more to the picture than meets the eye. ECM circulators are not smart pumps. They're not smart. They are obedient. They'll do what you tell them to do. They're programmable, and that's the key here. No matter what you think about ECM, these things are fundamental. We have to know flow, we have to know head, we have to know performance curves, and we have to know system curves. That's how they work. All right, that's how they work. They can adjust to certain things depending upon the type of ECM it is, but they don't take all this stuff into account, so you don't have to worry about it. So we're gonna kind of dive into that and make sure we understand. All right. Again, flow and head are fundamental. Flow and head are fundamental to what we're talking about. You cannot separate flow and head. Flow and head are tied together, and flow and head is how we size circulators, right? Here's an important thing about flow. A lot of people, when we talk about, it's 3 gallons a minute at 7 feet ahead, a lot of folks will tend to think that 7 foot ahead is a limiting factor. So no matter what, you're going to have 7 foot ahead. Well, no, flow and head are tied together. As flow increases, so does the head loss through that pipe. The pressure loss through that pipe increases because the pressure loss through the pipe is based upon the flow. The more flow, the more pressure loss, the more friction loss you'll have through that pipe. So as flow goes up, the head loss or the head pressure loss in the piping system goes up exponentially. It's a function of the increase, the square of the increase. We're going to show you how to figure that out. But as flow goes up, head will go up exponentially. And we come back to this guy an awful lot because it is fundamental to what we do. This is the universal hydronics formula. And we call it the universal hydronics formula because it's universal. It applies to everything. As much as people tend to dismiss this, it applies to everything. It's how we size stuff. It's how we troubleshoot. It's how we make sure things are working right. The universal hydronics formula tells us that GPM is equal to BTUH divided by the product of delta T times 500. Let's define the terminology here. GPM, of course, is gallons per minute. That is the flow rate you need your circulator to deliver in order to deliver the BTUs required. So GPM is the flow rate you need to deliver the BTUs required. All right, gallons per minute. BTUH, of course, is the heating load. It could be of the entire structure. Let's say you're doing a zone valve job. You've got one pump and a bunch of zone valves. That BTUH load is the design condition load of the entire house, because that circulator is going to have to deliver flow for the entire house. So that would be the entire house heating load. If it's a zone pump, well, then it's just simply the load of that pump on that zone. Could be 15,000 BTUs, 25,000, whatever, however many BTUs under design conditions that zone has to deliver. All right. Delta T times 500, okay, that's our denominator in our little division equation. Delta T is the designed for temperature drop of the fluid as it goes through the system, designed for temperature drop. It basically, what's our target here? What are we trying to accomplish? Typical residential hydronics will design to a delta T of 20. Sometimes we'll do residential radiant floor heating to a delta T of 10. Anybody have any ideas why we might do 10 degrees for residential radiant? If you have them, just type them on in. I want to see if we got our thinking caps on today. But we might do 10 degrees for residential radiant. Indirect water heaters are often designed around a 30-degree delta T. So it's our target. It's what we're shooting for. It's how we're going to design this. But if you have an idea why residential radiant's designed to a 10, type it on in. I'm just very curious. And then 500 is a mathematical constant that we use for 100% water. 500 comes from multiplying the weight of 1 gallon of water. 1 gallon of water weighs 8.33 pounds, times the number of minutes in an hour. Traditionally, that's 60, times the specific heat of the fluid. The specific heat of 100% water is 1, and the specific gravity of the fluid. Specific gravity of 100% water is also 1. So that's a lot of ones. 1 BTU to raise 1 pound of water, 1 degree Fahrenheit, 1 hour, et cetera, et cetera. If we multiply 8.33 times 60 times 1, we come up with 499.8. We'll call it 500. Good enough, right? It's a house. We're not flying this thing to Mars. We throw glycol into the situation, that number's going to change. It's going to get lower. The more glycol we put in, the lower that number gets. If we do like a 30% glycol, 70% water mix, that might go down to say 475 or thereabouts. You do a 50-50 mix like you might do with a snowmelt system, that might go down to 435 or thereabouts. So what you see is the more glycol you put in, the lower the 500 gets. The lower the 500 gets, the smaller the denominator gets. The smaller the denominator gets, the more GPM you're going to need to deliver the same amount of BTUs. That's how it happens. Colin's got it. We designed to a 10-degree delta T for Tootsie Comfort, right? For Tootsie Comfort. We want consistent floor surface temperatures, especially if we're putting tubing in between the floor joists or something like that. We want to keep the floor surface temperature relatively constant. So we'll tighten that up to about 10 degrees. You go into concrete slabs, yeah, most cases 20 degrees is fine. But anything outside of a 4-inch concrete slab, you're going to be looking at something like 10 degrees thereabouts. Very good, very good. Yeah, more even heat distribution, says John Bowden. Very good. All righty, let's do an example, a zone pump for a 30,000 BTU zone. Now, 30,000 BTUs, I don't care who you are or where you are, that's a pretty big zone. Maybe not in Fairbanks, but in most of the continental US, a 30,000 BTU zone is a big honkin' zone. So we're going to size a zone pump for a big honkin' zone, a 30,000 BTU zone. So we fill in what we know, 30,000 divided by 20 times 500. Another nice thing about 20 is 20 times 500 is 10,000. You can divide anything by 10,000, right? So in this case, 30,000 divided by 10,000, our gallons per minute flow rate, bada bing, bada boom, is 3 gallons per minute. That's what our circulator has to deliver. It has to deliver 3 gallons per minute. Very good, very good. Now, head loss. Head loss. Water goes through pipe, right? Water's going through that pipe. The water's rubbing up against the sides of the pipe. Okay, the water is hitting fittings and making turns and stuff. All of that is essentially what we call pressure loss through that piping, pressure loss. So head loss is really friction loss or pressure loss as the water rubs up against the sides of the pipe, etc. It's losing pressure as it goes through that loop. In order to keep that 3 gallons per minute going, we have to overcome that friction loss. The piping creates the friction. The circulator has to overcome that friction loss. Now we can math that out. It's a function of the flow rate and it's a function of the pipe size. And we'll show you how we can figure that out. Maybe a great way. I love this analogy. I show it all the time. I love this analogy because this is a great expression of what happens in a hydronic heating system. If you are of a certain age, and I want to know who out there is old enough to have remember playing with Hot Wheels in the glory days of Hot Wheels. I'm talking about the late 60s, early 70s.
Ooh,
I
ooh,
was,
ooh, ooh.
yeah, Jason, there you go, man. You still have yours, don't you? I know you do. Hot Wheels were fantastic, but in 1970, Mattel came out with the Supercharger, which was this little speed shack, that little orange roof. It looked kind of, at first I thought it was a Howard Johnson's. That tells you how old I am. But what that is was a little battery powered booster that had two little rubber wheels spinning inside. And before, you have to have your start of your Hot Wheels track up high and use gravity to go down and do a loop-de-loop and do a jump and all that other fun stuff. Now you didn't need gravity. Now you could lay it out on the floor like a big Indy car track, okay, just like you could do a big old oval, all right? And the way it worked is you connected the loops, you made a big oval, and that little thing was, the rubber wheels were spinning, and you'd take your little Hot Wheels car and you'd roll it on the track into the supercharger, and boom, it'd come shooting out the other side. And it'll go all the way around the track. It's slowing down, it's slowing down, it's slowing down until it got into the boom, and back into the supercharger and go out again. And gloriousky, what fun that would be. Okay. That to me is a great example of a hydronic heating system. If you think of the supercharger as a circulator, the orange track as pipe, and the car as water, you got what's going on here. The only difference is, instead of one car losing speed, you'd have to fill up the entire track with cars kind of nose to tail to get an idea, to get a more accurate representation of what a hydronic heating system would actually be. But the supercharger does the same thing. What comes in gets shot out at a higher velocity. All right. And what happens is the outlet part of the circulator turns that velocity into pressure. So whatever comes into a circulator goes out at a higher velocity / pressure. So great analogy, I think, for a hydronic heating system. The Hot Wheels are the water, the orange track is the pipe, and the supercharger is the circulator. All right. So that's cool. That's some cool stuff. Now, how fast do the little rubber wheels in the supercharger have to go, or how big of a supercharger do we need? Well, we know we need 3 gallons a minute. Our little green supercharger has to give us 3 gallons a minute. But now we have to figure out the head loss. And for head loss, there's a couple ways to do it. This tends to be the more accurate. This is a table from the Copper Tube Handbook that is published by the Copper Development Association. If you go to their website, you can actually download a PDF of the Copper Tube Handbook. It's about 150 pages of mind-numbingly boring stuff, highlighted by Table 6, which is pressure loss of water due to friction in types K, L, and M copper tube. And this gives it to us in PSI per linear foot, PSI per foot. So we'll have a little bit of math to do to turn that into head loss for an entire loop. Now, our flow rate was 3 gallons a minute. All right, at 3 gallons a minute, we're going to be using 3/4 inch type M copper. 3 gallons a minute fits right into our pipe sizing guidelines. 3/4 inch type M copper for our loop. All right, and we're presuming just a loop of fin tube baseboard at this point. So our pressure loss in PSI for 1 foot of pipe is 0.009 PSI. So it's 0.009 PSI pressure loss for 1 foot of 3/4 inch M at a flow rate of 3 gallons per minute. Now we have to figure out, how long is that loop? How long of a run do we have? That's, you can't get in there and measure it unless you're doing the install while you're doing it. I mean, and that's okay. What we do here is we'll estimate. All right. And the best we can do is to estimate as accurately as we can, which means, okay, I got to go 5 foot up, 10 foot over. That's 15 foot. I got to go down 40 feet. Okay, that's 55 feet. I'm going over 20 feet. That's 75 feet. I'm coming back 50 feet. That's 125 feet. I'm coming over 20 feet. That's 145. I'm coming down 10. All right, that's 155. We'll call it 160 feet to be safe. That's the length. Now we have to add for fittings, right? Typically for fittings, because you can't get in there and count them, we'll add 50% of that length to allow for fittings. All right, so whatever that your your estimated length is multiplied by 1.5, and that'll give you additional equivalent length for your fittings. It'll take your fittings into account for you. So for our purposes, our total equivalent length, including fittings, for this particular example is 285 feet. This is a big zone, people. Okay, this is a pretty good size zone. We got 100 and some odd feet of pipe, and taking all the fittings into account, it's equivalent of 285 feet. If I were to multiply 0.009 times 285, I come up with just under 2.6 psi worth of pressure loss. Now, here is a pop quiz for y'all. How do I turn psi into feet ahead? Type in your answer. Let's see what you got, man. 2.57 times something is going to give us our feet of head. How do we convert psi into feet ahead? Any guesses or thoughts or ideas out there? Let's see what you come up with, because I can't hit the button until I get at least one guess. All right. Use my phone app. Okay.
There, Robert got it. 2.31.
I'm sorry, but Michael's got the best answer there. I like that. But Robert got it. Yeah, you multiply by 2.31. Okay, you multiply your PSI by 2.31, and that'll give you the head loss in feet ahead for the loop. So in this case, I'll explain why it's 2.31 in a second. 2.57 PSI times 2.31 feet of head per PSI. All right, that's going to give us just under 6 feet ahead. 6 feet of head loss. So this big honking zone, 30,000 BTUs, 285 feet of equivalent length. This is a big zone, people. All I need is 3 gallons a minute at 6 feet ahead. That's it. 3 gallons a minute at 6 feet ahead. That's not a lot of pump. 007 standard efficiency can do that in its sleep. All right. It can do that in its sleep. That's why it's kind of university put it in. Don't worry about it. Now, why 2.31? Day one of plumbing school, when I was getting my plumbing license, we learned this, is that a column of water 28 inches high, would have a gauge pressure at the bottom. If I had a gauge at the bottom, it would have a gauge pressure at the bottom of 1 psi. 28 inches, a column of water 28 inches high would have a gauge pressure at the bottom of 1 psi. Now, another way of saying 28 inches is 2.31 feet. So I've got 1 psi per 2.31 feet of water column, so to speak. In other words, it will take 1 psi of pressure to raise a column of water 2.31 feet in the air. So somewhere along the line, instead of rating circulators in terms of psi for the pressure differential it could create, we came up with feet ahead for the pressure loss it could overcome. Too often people think feet ahead equals feet of height. I've got a tall building, I need a high head circulator. No. We don't take the height into account. It's the length of the run, whether it's horizontal, vertical, doesn't matter. We don't care about the height. Our static fill pressure fills and pressurizes that. All we have to do is overcome the pressure loss once the water's flowing. So if I multiply my PSI by 2.31, I'll get my feet ahead. All right, let me know if that makes sense to y'all. But in this case, now we're looking at 3 gallons a minute at 6 feet ahead. That's not a big pump. That's not a big pump. Let's say you're we'll get into selecting in a second. But once we know 3 gallons a minute at 6 feet ahead, we can start getting into some interesting stuff. We can now see where a system's actually going to operate. All right. Now we're going to get into something called system curves. Pump curves you know about. Pump performance curves, we come up with them in the factory. That tells us at these different flow rates, this is what a circulator can do. The circulator has this pump curve, that blue line that you see right there. That's the pump performance curve. That circulator can work anywhere on that pump performance curve, and only on that blue line, only on that pump performance curve. That's the only place. Once you put that circulator on a job, that's the only place that circulator can work, somewhere along the blue line. The reason we look at system curves, the red line, is so we can figure out where on that pump performance curve the system is actually going to operate. Pump curve we come up with at the factory. A system curve is a mathematical curve that you can figure out based on the actual system that you've installed, on the piping system. Every piping system has its own unique system curve. Remember, we said early on, Head is a function of flow. As flow goes up, head goes up exponentially. As flow goes up, head goes up exponentially. Where the system curve and pump curve intersect, that's where the system will work. Every single time, 100% of the time, it can't work anywhere else. All right, energy in equals energy out. The pump has to work on the pump performance curve. Bottom line, it can't go anywhere else. Once you put it on a system, that system will go where the circulator tells it to go. All right, I may need 3 gallons a minute at 6 feet ahead, but the minute I slap a circulator on there, I ain't going to get 3 gallons a minute at 6 feet ahead. I'm going to get what the circulator says I'm going to get. All right, that's an important thing to remember. That's where overpumping comes into play. The system's going to work where the circulator says. All right, so we have to plot the system curve to kind of get an idea. All right, and you may never do this in the real world, but what the importance of it is just knowing that it exists and knowing what it means. Okay, how do you plot a system curve? Well, fortunately, there's a math formula, and I know how everybody loves them some math. All right, well, I'm going to show you 2 ways to do this. That's just going to be the second way you're going to like a lot more, but the first way is just it is a mathematical relationship. Okay, this is the formula for plotting a system curve. Head 1 divided by head 2 equals flow 1 divided by flow 2 squared. Oh, I bet you're just loving this, right? Does this mean I got to do square roots and stuff? No, you don't have to do square roots or anything like that. Just got to do a little algebra. This is 7th grade algebra, more or less. Now, we understand that we already know flow 1 and head 1, right? Flow 1 is 3 gallons a minute. Head 1 is 6 feet ahead. We know flow 1, we know head 1. Flow 2 is a variable that we will input. So I know at 3 gallons a minute, this piping system gives me 6 feet ahead. What would the head be at 6 gallons a minute? That's the question. So for flow 2, I can put in 6 gallons. I can put in 6, and then using algebra, I can figure out what head 2 would actually be. All right. So flow 2 is a user inputted variable. So I could do, I know 3 gallons a minute. I could put in 1 to figure out what the head would be at 1 gallon a minute. I can put in 2. I know 3. I can put in 4, 5, 6, whatever else I want. I do those math formulas for each one. And then I've got different points on a plot. Remember, was it 5th or 6th grade math? You had to do, charts and graphs, and you had to figure out different points on the plot, and then you put them on the plot, connected the dots, and you made like a butterfly or something silly like that. And you figure, and I'm never going to use this in the real world. This is a monumental waste of time. Well, today's the day, people. Today's the day we're going to use it. So we know 3 gallons a minute is 6 feet ahead, right? Flow 1, head 1. Let's figure out what the head would be at 6 gallons a minute. So head 1, 6 divided by head 2. That's X. In algebra, that's X. That's going to equal flow 1, 3 gallons a minute, divided by flow 2, 6 gallons a minute, squared. Let's simplify. 6 divided by X equals, 3 divided by 6 is 0.5. It equals 0.5 squared. All right. So 0.5 times 0.5 is 0.25. So 6 divided by X equals 0.25. Now we want to start to isolate things. So I'm going to multiply. I want to start to isolate my X. So the first thing I'm going to do is multiply both sides by X. So I'm not dividing, I get that division out of the way. So if I multiply both sides by X, I get 6 equals 0.25X. Now we solve for X, we divide both sides by 0.25. And what I find is the head loss at 6 gallons a minute is 24 feet ahead. I double the flow. What happens is I double the flow. The head loss goes up 4 times. All right, the head loss goes up 4 times. Double the flow, head loss goes up 4 times. So at 6 gallons a minute, it's 24 feet ahead. I can apply this same math formula to all the different flows, come up with my different points on the plot, put them on the plot, connect the dots, overlay my pump performance curve, where they intersect, voila, that's what I got. All right, here's an easier way. Tip of the cap to Bell and Gossett. This is the Bell and Gossett system sizer wheel. And if you look right here, you'll see a reproduction of the hand-drawn original B&G system sizer wheel drawn by Gil Carlson, who is Bell and Gossett's director of engineering for Lord knows how long. But he drew this up as just something for himself to create, to help, as a shortcut to make the math a little bit easier. And somebody saw him with it and he just kept in his desk for himself. Someone from the marketing department saw him with it, and he goes, "What's that?" He told him, he says, "Wait a minute, we could make this something useful." And that's the birth of the B&G system size wheel. It is also now an app that you can use. But scale number 5 works out really easy. If we know in the white window, I've got my flow, 3 gallons a minute, and I've got my head 6 feet ahead right here, 3 gallons a minute, 6 feet ahead. I don't have to do any more math. All I got to do is say, okay, let's go right up to 6 gallons a minute. 6 gallons a minute, I see 24 feet ahead. Hey, 5 gallons a minute, I've got 17 feet ahead. 4 gallons a minute, I have 11 feet ahead. 3 at 6. 2, I've got a little less, I got like 1.7, thereabouts, 1.8. 1 gallon a minute, I've got 0.7. All right. As you can see, I can, just by lining up the flow and head that I know, I can figure everything else out thanks to the beauty and the genius of Gil Carlson. All right. So that makes it a lot easier. So these are my different head losses. So 1 gallon a minute, it's 0.7, 2 gallons a minute, 2.8, 3 GPM, 6 foot, 4 gallons a minute, 11, and so on and so on. Now that I have that information, let's just put them on a chart. All right. And away we go. Now they're all on a pump. They're all on a chart. Okay. They're all on a chart, and you can see it's kind of a hockey stick. It goes shoom, like so. From that, we overlay the pump performance curve and where the 2 lines intersect. We connect those dots to create the system curve. We overlay the pump performance curve where the 2 lines intersect is where the system is actually going to work. So let's say we were looking at 3-speed options, 3-speed standard efficiency options, the Takeo 0015, which is a steeper curve, 3-speed circulator, essentially the same pump curves as all the other 3 speeds that you're familiar with out there. The B&G NRF, was it the NRF 22? I think it's the NRF 22. 22, yeah. The Grundfos 1558 and some of these other ones. They're all kind of the same pump curves. The 0010 is a little unique. The 0010 is a flat curve pump that was built it was designed to be a replacement for the B&G 100. Now, if we look at our curves here, our points on the plot, I've got 3 gallons a minute at 6 feet ahead right here. We're looking at low speed. You pick either one of those circulators at low speed, and you're fine. You're fine. Another pop quiz for the group. When we started this, 30,000 BTUs, 285 equivalent feet. How many of you thought we could have done this with a 3-speed circulator at low speed? I want an honest answer from everybody out there. Because usually when you have a 3-speed circulator in your hands, where does that dial go? All right. Where does that dial go? It usually goes wham, right to high speed, which we call contractor no callback mode.
Well, Robert's starting at medium, and then
Robert's
if it doesn't work, then he switches it up to high. Yeah.
There you go. Robert, yeah, man, you got commitment issues, man. Go all the way. Go high, brother. Go high. There you go. No, that's a good call, Yeah. So, yeah, high. Yeah, okay, high. Yeah, which is cool. But we can do low. Yeah, ramming speed, says Michael Clark. Ramming speed. But think of that. Low is plenty. With either circulator, low is plenty. Here's the thing. If we did go high, we would actually be running every time that circulator came on, whether it's in April, whether it's in October, whether it's in January, okay? Whether it's in January, every time that circulator comes on, we're pumping at almost 5 gallons a minute, all right? Well, let's call it just a little, let's call it 4 3/4, all right? That's a good bit more flow than we need. If we flow at a higher flow rate than we need, what's going to suffer? The delta T is going to suffer. So in this case, that delta T is probably going to be in the low teens, maybe 12. All right, maybe 12 to 13 degree delta T instead of a 20. If we have a 12 or 13 degree delta T instead of a 20 degree delta T, under design conditions, because that's the best it's ever going to be, right? Under design conditions, I've got a 12 to 13 degree delta T instead of a 20 degree delta T. What's going to happen? All right. That's a question for the audience. Type in your answers. What's going to happen if I have a 10 to 12 degree delta T as opposed to a 20 degree delta T? What's going to happen? That's the question. So let's say it's a mod con boiler, and I want the water going out at 140, coming back at 120 under design conditions. It's not going to come back at 120. It's going to come back at, let's say, 128. What's going to happen? Colin's got it. Yeah, we're going to have some short cycling. That boiler's going to short cycle. A boiler that wants to short cycle anyway is going to short cycle a little bit even more. Another thing, instead of having 120 degree water, we're bringing back 128. If it's a condensing boiler, are we going to have, is it going to condense all that much? Not really. It's not going to condense as much as it could or should, right?
Just thinking about it.
Yeah, it's just thinking about condensing. Do I want to condense? Maybe a little bit. No, I don't know. You know, it's kind of right on that shaky little line. So we are impacting the efficiency of that system dramatically under design conditions simply by going click, click. I don't want to worry about it. I know this will work. No one is going to call me back and say they're cold, which is true. No one's ever going to call you back and say that you're cold, that they're cold, and it's your fault. And no one's ever going to call you back and say, hey, bucko, you promised me a 20 degree delta T. It's only 12. Get your butt out here and fix it now. You're never going to get that phone call either. What's going to happen is the system's never as efficient as it could be or should be. And you might be, because you're short cycling like crazy, you're going to be wearing out parts maybe prematurely. So 3-4 years down the road, something goes wrong with the blower motor, the ignition module, or something in that boiler has gone wrong, and you got to go back and fix it. And it's a healthy repair cost. And you're left with saying, yeah, we've had nothing but problems with these boilers. That's really why we don't sell them anymore. Oh, thank you for that. You know, that's great. So those are some of the things that happen. Yeah. Lower delta T, longer time to satisfy? Not really. The lower delta T, lower delta T, higher average water temperature, it might actually satisfy a little bit quicker, which again, short cycle brings the short cycling into account even worse. And ladies and gentlemen, this 12 degree delta T or 13 degree delta T we're talking about, that's the best scenario you're ever going to see. As it gets warmer out, the BTU load goes down. I'm still pumping at the same rate. That delta T is going to get smaller and smaller and smaller to the point where I would guess most of the heating season, you're going to have a delta T less than 5. That's not good for anybody. Just saying. All right. So interesting discussions. Now, how does ECM play in all this? If I'm using ECM, I don't have to worry about any of this, right? It's variable speed. No, it's not variable speed. Is not the answer here. Remember, you're not Harry Potter. Ron Weasley doesn't work for you, and you're not dating Hermione Granger. Okay, it's just not happening. All right. There is no such thing as magic. People call these things the magic pumps and all that. It's utter nonsense. There's no such thing as magic. We're still talking about system curves, and in this case, control curves. ECM they have a lot of pump curves, but we choose a control curve to make it work. All right. So we can't get away with that. We can't get away from that with ECM circulators. They don't size themselves with a little asterisk there. A lot of people, I just stick it and push the button and it takes care of itself. It's automatic, right? It says auto right on there. That should take size. It doesn't work that way. We're going to discuss that, but they don't size themselves with an asterisk because there is one sort of exception to that. And we're going to talk about both delta T and delta P. Dave, we got questions? Anything that we need to address in the interim, Dave and Jason?
Well, a couple questions came in from Robert, who was asking, if we had a lower delta T, we'll get a longer time to satisfy the stats. Well, yeah, and that's what we want, right? When it comes to hydronics, we want to do a slow and gentle heat. We don't want to do a fast and furious. So by widening that delta, having that delta T, it's also that difference that you have in the system. And then he was also talking about, you don't have enough BTUs, you're losing some, they're going back. Exactly. When we have that small delta T, more BTUs are heading back to the boiler. And by moving it faster and a lower delta T, it's all starting to compound itself on top of each other. So we want to, we would love to match the BTUs to the actual heat loss.
Mm-hmm.
That's what we're looking to do. So by not over pumping a system, if we can only deliver what the room needs, that's when we start getting better and better out there. Yes.
Yeah. And the thing is with our universal hydronics formula, the equation equals out. So the delta T, I have to satisfy heat load, right? And at a 20-degree delta T, I need 3 gallons a minute. If I give it 6, I'm only it has to balance out. 6 gallons a minute at a 10-degree delta T is going to equal 30,000 BTUs. You know, I know it's a math formula, but it's science. It's how these things actually work. You know,
Right. Yep. Go ahead. Go. Sorry.
I've had people say to me, "Oh, the system's going to do what the system's going to do." You know, I don't know what you're saying. The system's going to do what the system's not going to do what the system's going to. The system's going to do what the circulator tells it to do. You think about that. The circulator, the boiler makes the BTUs. The heat emitters deliver the BTUs. But what's facilitating the journey? It's the circulator. Circulator's in charge, man. Once you throw a circulator on a job, all your math kind of goes out the window, sort of, provided that's why you want to do the math, make sure you have a circulator that can handle the job. But once you throw a circulator on there, the system's going to do what the circulator says. Like I said, you're going to get, if you threw that 3-speed circulator in on high on that system we just showed, I'm going to get nearly 5 gallons a minute all the time. So it's going to work at 5 gallons a minute all the time. It doesn't matter what the system needs. That's what the circulator is going to do.
Are you coming? I don't remember the rest of the presentation here. Are you coming back to your system sizer at all?
No.
Okay. So every time we do this class, I also get a bunch of emails after the fact. People can't find that system sizer. All right. Or trying to get their hands on it. It's not an easy thing to get your hands on. I do want to point out one other thing that they also have. And let's see if I can get it to focus properly. There we go. So you can download an app. All right. And so they do have the app by B&G as well. All right. I'll turn it straight up. Sorry there. And you type in your known flow and head, put in your unknown, and then just hit the enter button at the bottom of the screen there. And you'll see it. Oops, what'd I do? Nope, sorry. 6, enter, and then you'll see that 24-foot ahead that John was talking about before.
Yep.
So I just wanted to let everybody know that there is an app also to download, because I inevitably get a bunch of comments on, can't get my hands on one of those things. Yeah, they're really hard to get.
They are hard to get a hold of. Yeah. And I'll tell you, hats off to B&G and Gil Carlson. I mean, this was one of these seminal pieces of not equipment, but accessories that makes everybody's life a lot easier. I use mine all the time, and it's again, tip of the cap, tip of the cap to the competition. They did it's a great thing they did for the industry. So, all righty.
Hey guys, before you guys get going, Michael Clark is asking here, does the same logic apply to indirect water heaters? I want to dump that heat into my DHW as fast as possible. Now we're looking at a different scenario there with different delta T's for the indirect requires, right?
Right. Again, we're not talking about speed of transferring. We're not talking about speed of transferring heat. It's the flow rate of the water. GPM is gallons per minute. BTUH is BTUs per hour. Those two things. I cannot, unless I change temperature, I can't make an indirect heat exchanger exchange faster.
Yeah.
All right. That's why, again, we designed to a 30-degree delta T with an indirect tank, primarily because of the pressure loss through the coil. Okay, it's still going to be the same. We're not going to make it go faster just by pumping it faster. It's still going to be, it's still gallons per minute and BTUs per hour, and there's a limited. We can only change, exchange the heat only so fast. Right, it can only absorb only so fast. That's why when we talk about rate of recovery and indirects, okay, it's based on BTUs. It's not based on the pump or anything. Just based on BTUs. All right, cool. That's a great one. And that's going to be a future webinar right there, Michael. I think that's a future webinar right there. All right. One of the things with variable speed ECM technology, all of them have a constant pressure mode. So if you have a zone valve job, we're talking constant pressure mode. What does constant pressure mean? It means that when you set this thing up in a constant pressure mode, you select a setting. it's going to be what we see here, this red line. It'd be the ultimate flat curve pump. It will adjust its speed so that circulator is always creating 10 foot of head pressure differential. Okay, it's the ultimate flat curve circulator. Now those green lines, those curved green lines, diagonal green lines that you see, those are programmed into the circulator itself by computer, by a technician who did all the programming. There's a bunch of different performance curves. Each one of those is a different performance curve at a different speed. So we've got dozens of these things built into the circulator. So they're all different all different pump performance curves. The 10 foot of head constant pressure is what we call a control curve. The control of the circulator says no matter what, we're going at 10 foot of head constant pressure. So let's say I've got a zone valve job that requires 7 gallons per minute at 5 foot ahead. Okay, it's not an uncommon. It's within the realm of reality. 7 gallons a minute at 5 foot head. This is what I need, right where my cursor is right here. That's what I need. All right, but because I've put a circulator in there that has 10 foot, that's constant 10 foot ahead constant pressure, I'm never going to work it. I'm never ever going to see 7 gallons a minute at 5 foot ahead. I'm always working right here with all zones calling, and that's going to be about 9 gallons a minute at 10 foot ahead. So almost probably a 28%, 30% over pump from 7 to 9, probably just about maybe just almost 30%. All right, so that's where it's going to work with all zones calling. Now, how does a variable speed circulator know to vary its speed? There's a lot of ways to explain it. The way I can, the way I understand it best, and therefore the way I can explain it the best, is it's pressure or resistance against the impeller. So say I've got 5 zones open, right? And my impeller's spinning like so. One zone closes. So instead of 5 holes for all that water to go through, I only have 4. That impeller is going to feel as though it's pumping against a little bit more resistance. Okay, it's going at a certain speed, but instead of having 5 holes for that water to go through, it only has 4. It's almost feeling some back pressure is the wrong word, but it's feeling a little bit more resistance. That is a signal. That is a signal for that circulator to do what? It's the signal for that circulator to slow down. All right. I don't have to do as much work. Therefore, I can slow down to maintain that 10 foot ahead constant pressure. So it's going to look kind of like that. All right. In reality, when that zone closes for like a nanosecond, we're going to work on that same pump performance curve up here, okay, where you see my cursor. It's actually going to work up there. The impeller senses that resistance. The brain interprets the amp draw and says, no, 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 no. We're not working up here. Bam, we're going to go right down here and stay at 10 foot ahead constant pressure. And it's going to happen like in a nanosecond. It's pretty quick, but that's the process that it goes through. Another zone closes. We're pumping against a little bit more resistance. So we have a new system curve. All right. Pump's going to go slower still and slower still as zones close. So whereas I was working on this up here on this performance curve at, let's say, 35 watts, okay, max speed is 44 watts, instead of working on this performance curve at, let's say, 35 or 30 watts, now I'm going to work down here at, say, 20 watts. So the operating range is going to be between 20 and 30 watts as zones open and zones close. I'm going to go ramp up from 20 to 30. All zones call, I'm at 30. Zones close, I ramp back down to 20. All right. Instead of, let's say, a standard efficiency circulator that would be working at 80 to 85 watts. Okay. So that's how they save electricity, and that's how they operate and go faster or slower. All right. So that's with a 10 foot ahead constant pressure setting. Let me know if that makes sense to you, because that's kind of important. Again, here's an illustration of, let's say, the 007E, the ECM version of the 007. 10 foot ahead constant pressure. That's where it operates all the time. At full speed out here, we're at 44 watts. But again, as zones close, we move down and start to use fewer and fewer watts. Okay. So as a zone pump, a lot of people think about, well, why would I use an ECM variable speed circulator as a zone pump? It's not going to vary its speed. For the delta P circulator, it changes its speed based on changing pressure differentials in the system. That's zone valves opening and closing. If I don't have zone valves, if it's simply a zone pump, nothing's going to ever change that pressure differential. So why use an ECM circulator as a zone pump? Sounds logical, right? Well, we have the ability to do a few things to get closer to where we need to be. So again, 3 gallons a minute at 6 feet ahead, that zone that we just did, that's where I need to be. In fact, at 4 gallons a minute, I'm going to be at about 11 feet ahead, but it's not going to work there. It's actually going to work right here, a little under 4 gallons a minute. That's a little bit better than where we were with that 3-speed circulator set to max speed, if you'll remember. Okay, so it's not a bad choice. It's not a bad choice at all. We'll be working at lower wattage, and we'll be a little closer, and we'll keep that delta T as wide as we can for as long as we can. Not the perfect solution, but a better solution than a 3-speed pump at high speed. The 003, our 0015E3 is a 3-setting variable speed circulator. This gives us some options. We have low at 5 foot ahead constant pressure, medium at 10 foot ahead constant pressure, and high is full speed fixed speed. There's the system curve kind of plotted out for you. What setting would you select for the 0015E3? This is I want to throw this out to the audience. What setting would you choose here for the 0015E3? Low, medium, or high? I need 3 gallons a minute at 6 foot ahead. Type in your answer. I'm very curious as to where we are as a family here on our decision making. So type that on in. I know some of you are thinking and thinking and thinking. Do you go low? Do you go medium? Do you go high? Let's see. What do you got? What do you got? I'm waiting, people. I'm waiting.
Low.
You got Robert with low. Good call, Robert. I'm with you 1,000%. Low is good. I know I need 3 gallons a minute at 6 foot ahead. Remember, we still kind of estimated a few things, didn't we? Right? And when do I need 30,000 BTUs? That much of the heating season. And the worst thing that's going to happen here, let's say all my calculations were dead on accurate, absolutely dead on accurate. The worst thing that would happen here if I went with low is that under those design conditions, as long as I have the horsepower in the boiler, my delta T is going to get just a little bit wider. Maybe it'll be 22 degrees, 23 degrees under design conditions instead of 20. The worst things have happened. I'm still going to be able to heat. I'm just going to have a little bit wider delta T. Not a bad thing. Is the 007E fixed to 10 foot ahead? Yes, it is. It's simple, no programming. It was designed to simply be the ECM complement to the 007. So yes, it is fixed at 10 foot ahead. Is that right? Let's take a quick look at delta T now. Delta T pumping. This is a little bit different. Delta T pumping, and it's currently our VT2218. We'll have a new updated version of this next year that I think is going to be really exciting. Remember we said circulators don't size themselves. ECM circulators don't size themselves, but there was those asterisks behind it. The 2218, that's the asterisk. All right. This is as close as we have to a self-sizing residential circulator in the marketplace today. It's as close as we have. What it does is it will vary its speed in order to maintain your designed for delta T within the system. So you can program this. It comes out of the box programmed for a 20-degree delta T. All right, you design your system to a 20-degree delta T, you slap this thing in, comes with 2 sensors, one on the supply and one on the return to sense the delta T of whatever it's going through. All right, slap those sensors on. What's going to happen? It's going to run until it gets to a 20-degree delta T. That's pretty much self-sizing. So it's going to self-size itself for the most part. So if I need 3 gallons a minute at 6 foot ahead, and it is design conditions, all right, it's going to run until it finds that 20-degree delta T, and it's going to say, all right, 3 gallons a minute, 6 foot ahead, I'm going to run right about here, which is maybe 20% of its maximum speed. Line A is minimum speed. It doesn't go any lower than that. And line B is its maximum speed. It can't go any faster than that. As long as you're somewhere within that green wedge, it'll find it to maintain that 20-degree delta T. Now, let's say it's a zone pump. Is it always going to work there? No. It's going to change its speed as a zone pump. All right, it's going to change its speed as a zone pump. Here's my question for the group. How will it know to change its speed as a zone pump? What's going to tell it to change its speed? And I'll give you a hint. We talked about it already today. It's a formula that guides the universe. There's a hint. How is it going to know to vary its speed as a zone pump? Zone valves, we know. Zones open and close, right? That's going to change the delta T. I don't need as many BTUs. Yeah, it's going to go slower, right? As zones close. How is it going to know as a zone pump to change its speed? Demand, load. I think what you mean is load. BTU load. As it gets warmer out, the BTU load's going to go down, right? As it gets warmer out, the BTU load's going to go down. It's not as cold out. How do we infer that? Well, I don't have to deliver as many BTUs to the system, right? As it gets warmer out, the delta T is going to want to start to get smaller because I'm not yanking as many BTUs out of the loop. It's going to want to get a little smaller. The sensors say, hey, that delta T is getting smaller. The pump's going to say, all right, I know what to do. I'm going to go slower to make sure I maintain that 20-degree delta T. It gets warmer and warmer and warmer out. I'm going to go slower and slower and slower until I hit my minimum speed, which is 9 watts. In this particular example, 3 gallons a minute at 6 foot ahead, I'm going to say 60% of the heating season, it's a fixed speed 9-watt circulator, and that ain't bad. All right. We may not have a 20-degree delta T in March, but we're not going to have a 4-degree delta T. That's the important part. All right. We're going to make sure we maximize the system efficiency to the extent that we are able to. So that's why delta T makes sense as a zone pump. As a zone valve pump, it makes even more sense. Okay. And the bigger the system, the more sense it makes, because I've got in this case, 3 gallons a minute at 6 feet ahead. I'm using about 20% of its capabilities, really, if you think about it. I'm not getting a lot of variable speededness as a zone pump. Doesn't mean it's bad to use. It just means, okay, am I getting the most out of it here? The bigger the system, the more variable speedosity we're going to have. Is that a word? I guess it is now. The more variable speedosity we're going to have, and I'll be able to use more of that circulator's capabilities. Here, for the most part, I got a fixed speed 9-watt pump, which isn't bad. It isn't bad. And if I have it in a zone valve job, let's say 8 gallons a minute, 7 feet ahead. Here's an example of a larger system, all right? 8 gallons a minute at 7 feet ahead. This is my maximum speed. As it warms up or as zones open and close, I'm going to bop up and down between minimum speed, and this would be my maximum speed. I'm just going to bop up and down between those two. And minimize my electrical consumption, which the U.S. Department of Energy says delta T operation and control is the most electrically efficient way to run a variable speed circulator, and again with assisting that system in making sure that delta T is as wide as possible for as long as possible. We'll make sure we enhance the efficiency as well. All right, whew, that brings us up to 1 full hour. How about that, man?
Awesome.
That was pretty
master class in estimating and calculating head and flow.
I guess my question to you guys, my question to the audience in particular is, does this help illustrate the importance of circulator selection for you? Because remember, it's easy to oversize a circulator and the downsides aren't all that bad, to you. What the end user will experience is a system that's not as efficient as it could be or should be, or as was promised. All right, that's number one. And number two, we're kind of building in little service time bombs that will wear out. They will wear out components before too long. So that's why it's important. It's not because people are going to freeze to death and blame you. It's that the system's never as efficient as it could be or should be. And Dave, you know this, and Jason, you'll learn this, is our tech services department. It's one of the more common calls they get is, this system's not as efficient as I thought it should be or thought it was going to be. It's still better than what I had, but what is there something wrong? That's the most common question we get from homeowners. It's just it's not that the circulator's wrong. It's not that the boiler's wrong. It's a bad match between the two. Oversizing is chronic because we didn't have any way not to oversize for generations. Now we do. We have delta T, we have delta P, and if we understand how to use them, we now can impact that oversizing. We can make sure we're sized more appropriately. We may not get them perfect, but we can get them better. residentially, and that can have a huge impact on how systems operate. We can make sure we don't short cycle, and Robert pointed out, we can make sure we condense as much as possible with a condensing boiler. And I tell you what, guys, you get into air to water heat pumps, this is even going to be more important. This is going to be even more important. All right, time for questions. Anything, questions and comments? Anything you guys want to add? And folks out there in webinar land, this is your chance to ask some more questions on today's topic or anything else you'd like to rap about. First off, let me ask you guys a question out there in the audience. Was this useful? Was it simple? Is it something you can work with? Is it something that you can employ? You can start using when you in designing jobs starting tomorrow. I guess that's a question I would like to know from you guys out there in the audience. Oh, we got an absolutely from Robert. Excellent. Thank you, man. That's very good. That's very good. All right. Chris says, perfect. Most certainly. Great, great, great. That's it. Again, that warms our hearts why we do these things. To just show you what's going on, and hopefully it'll help. Hopefully it'll help. Dave and Jason.
Yes, I do want to bring up a couple of things. The next Takeo Tuesday is not next week. It will be August 5th. We'll be jumping it back over to the commercial team. And they're going to be discussing variable chilled water plants. So,
oh boy,
yeah, I think that's going to be a pretty well attended presentation from the boys on the commercial side, from Rich, Brett, and Tony. So, the title was All Variable Chilled Water Plants. Topics include trends, chilled water system evolution, the reality of constant primary variable secondary, design concepts, and of course, the very end, what can go wrong?
What could go wrong? What could go wrong?
Yep. So that's the next Takeo Tuesday on August 5th. If you haven't registered yet, make sure you register. Yes, we'd like to do those individual registrations, and that just allows the PDHs to be sent out for you to get the reminders that we've got the class coming up and also the stuff in between. So.
And Dave, I understand something pretty cool is coming up tomorrow.
Yes, tomorrow night, something new.
What's coming up tomorrow?
New, something old, and doing a complete 180 and bringing us right back to the beginnings. So tomorrow is going to be our Takeo After Dark summer sessions start. And it's going to be, if you've been to, obviously you've been to Takeo Tuesdays like this, and if you've been to Takeo After Dark, a little bit different, same idea, a little bit different. But what we've got going on is the next generation of Takeo After Dark, and it's going to be a blend of our Monday Night Live that we used to do on Instagram Lives, which was not a presentation, it was a discussion and with some guests in there. So we're going to be doing this starting tomorrow night, 7 p.m. Eastern, and we're going to obviously still have that training portion, but it's going to be a little bit smaller, and it's going to be, you know, it's something a little bit different. It's a blend of Monday Night Live, Takeo After Dark, a podcast, all this stuff in between. We have picks from the field. It's all rolled into one. You can't ask for a better night. Yeah.
And what platforms are we streaming on?
Oh, that's the key right there, Dave. You forgot that part.
We complete each other's sentences.
That's why we hired you, Jason. You complete us. We are going to be streaming this live. Oh, Dave, did you want to say it?
No, come on. Let the man go.
Jason roll with it.
Go, Dave. Go. Yeah. No, go ahead, Dave. This is your baby. I want you to go ahead.
All right. So it is going to be here as well. So it is going to be on GoToWebinar. So if you're used to GoToWebinar and you want to go there, great. If you want to sit on the couch and use your phone, hey, we're going to be on Facebook Live. We're also going to be on YouTube live, as well as LinkedIn. So all 4 platforms will be at the same time. You just on the streaming, you want to follow the Takeo pages, not any of our personal pages. You want to be on the Takeo pages, and then make sure you register, or at least not register. Make sure you get notifications of when we go live, so you'll know when we kick in. But it is going to be 7 o'clock tomorrow night that we'll be kicking that off.
Live on Facebook, live on YouTube, live on LinkedIn. This is my dream. I always wanted to make a live double album, you know, like Little Feat Waiting for Columbus or something like that. You know, I've always wanted to do that, but I have no musical talent whatsoever, and I can't sing, and I ain't good looking. So this is my last shot, man. This is my last shot.
Love to see the YouTubers out there. I'll be monitoring the YouTube chats and questions. So let's see those YouTubers get involved.
Oh yeah, that's it. Yeah, live chat is available on all of those platforms, and we'll be monitoring all of those. So it's going to be it's going to be a hoot. It's going to be something different, something fun, and just take us into a new direction going forward. So we're really excited about it. So hopefully you guys can join us. We'd love to have you. What better way is there to spend a Wednesday night than with us?
Come on,
Right?
what else are you doing?
All righty, folks. Well, hey, thank you so much for the gift of your time. We do appreciate being able to spend this time with you today on Wednesday, on Taco Tuesday, Taco Tuesday. And join us tomorrow night. We'd love to see you there. We're also going to be giving stuff away, too. We got a lot of prizes.
What?
I know. Big prize time. You want a 0070? You might be able to win one tomorrow night. Just saying. So we'd love to have you there. It's going to be something new, different, and I hope you like it. I think you will. I hope you like it and find it useful. So thank you, Dave. Thank you, Jason. Always a pleasure.
Thank you, JB.
And thank you, everybody out there. Have a wonderful rest of your day, and have some fun out there and sell some circulators. We'll see you.
See you all. Enjoy.